Welcome to today's webinar titled Hong Kong UrbanNav, an open source multisensory dataset for benchmarking urban navigation algorithms, based on a paper published in the winter 2023 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Dr. Li-Ta Xu. Dr. Li-Ta Xu received his Bachelor of Science and PhD degrees from National Cheng Kung University, NCKU, Taiwan, in 2007 and 2013, respectively. He is currently an associate professor in the Department of Aeronautical and Aviation Engineering, AAE, at the Hong Kong Polytechnic University, PolyU. In 2023, he was a visiting research scientist for Google. He is an associate editor of Navigation, the Journal of the Institute of Navigation. His research interests are urban GNSS positioning, indoor positioning, and multi-sensor integrated navigation systems. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. Following the presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We will now turn the time over to Dr. Xu.
Thank you, Beth. So can everyone hear me clearly? I bet you can. So first of all, thank you for inviting me to give this webinar, and thank you guys to join me this morning to listen to this UrbanNav, and thank you for your interest. So first of all, before I start to talk about the data set, I would love to shout out to my colleagues, Darren and Ivan, Guohao, Yihan, Xiwei, and Wei Song. They are the real engine behind this data set. I mean, we only presenting like a 4 to 6 data set in this UrbanNav, but it's a lot of work, starting from building the computer, attach all the sensor calibrations, and run thousands of tests, and we pick up this 4 data set to share with you. So I would love to say thank you to all my colleagues. And this is my data. Like we have urban class, medium class urban, the urban, harsh urban, internal. We're going to provide you camera data set, point cloud data set. We also provide you sky mask. So it's a fun data set. I hope you will like it. Okay, let's get going. Benchmark are super important to foster R&D. I bet you all know, especially for those of you working in industries. Like Google has been releasing a smartphone data set starting from 2021. A lot of good data, good research has been published and been benchmarked in IO and GNSS conferences. For example, Taro Suzuki's FGO, TDCP, has been really fostering the industry and also academic field. So this is super important. And not only in GNSS field, in robotics field, we have Kitty. So this is a very famous data set for doing LiDAR slant, vision slant. It's really a huge part of this slant technologies. And also for Waymo, they have also opened the data set for perception. So this is super important to the field. So as a passionism of urban navigation, so I love to do something for the field as well. And I start to talk with ILN and also IAG. So we have a joint working group. So this 4.1.5. So we have some objectives. The objective is to open source multi-sensor positioning that collect in Asia Pacific, urban Kenya, because in these areas we have a lot of cities, Tokyo, Taipei, Hong Kong's, and like San Francisco, with lots of areas in this Asia Pacific region. So very important for us. And we want to raise the awareness of the urgent navigation requirement in highly urbanized areas, especially in low city I mentioned. And then eventually we wish the data set itself can play a benchmarking method for positioning and sensor fusion algorithms. So that's the goal. That's the goal. And we all know that most of the economic activities are in urbanized cities, and positioning our navigation are very important for that. Like this is Hong Kong. Hong Kong has been trying to compete with Singapore, being the best smart city and incorporating these new technologies. So what happened here? So we need to using a lot of smart devices, like Uber Eats, the smart device apps, and the reason FSD from Tesla as well. So you need very accurate and precise and robust positioning for these L2 vehicles. And of course, for L4 Waymo, this is all very important. So these applications require very accurate, robust, and precise navigation services. So looking at the challenge for the sensors. So for GNSS, we all know like not only the regular challenge that we have in open sky, those corrections message, but in urban we need to tackle with the multipass and unloss, two very different effects. So this has to be tackled. And for vision sensor, you're doing visual odometry or vision slant, you may encounter the image blur because in the city in the nighttime you have a lot of neon light when driving fast. It's easily you have a photo looking at the right hand side, right? So this is really blurred. It's really a challenge for getting this visual feature. And some dynamic objects running around is also a problem. And sometimes you have the repetitive features. That's also a big problem as well. For LiDAR, relatively a bit easier, but still high dynamics, dynamic objects and repetitive features are also challenges. So most of these very popular sensors they're using in either robotic or smart devices, they are challenged in this area. So it's really interesting to see what kind of algorithm we can come up with, fusing all of this or just trying the best for each of these to get the best performance. And now we're talking about UrbanNav. So in fact, in UrbanNav, we have two data sets. We have a Tokyo data set and a Hong Kong data set. So for the audience, if you would love to contribute even more data set, so we'll be very happy to host the data and trying to promote this for you. So please do contact me if you do have the interest to share your data set. So for Tokyo data set, it is led by Dr. Taro Suzuki and also Professor Nobuaki Kubo. So in my today's talk, we're going to focus on the detail of the Hong Kong data set in terms of the platform, sensor, calibrations, format, and environment that we have in detail. Okay, that's all about today. So starting with the platform, sensor, and data. So this is our Hong Kong platform. So if you can see this on this right-hand side. So this is the rack that we designing from the scratch, from the CAD drawing and ask a machinery to help us to do the precise manufactures. So in this platform, what you can see over here is that we have LiDAR here, we have a stereo camera here, we have IMU here, and we have span system over here. So we're trying to align the lines horizontally to help us to easier get a better extrinsic parameter between these sensors. So it means XY relative the same. And but we found out there's an interesting thing is that after you put the IMU here, it's very difficult to detach this one. But yeah, if you want to design another one, I suggest you make the run a bit higher. But this is what we do. So we have this one. So and in this data set, we have the 32 LiDAR and the stereo, IMU, and span. I will talk about the detail of these sensors later. And we also have the LiDAR 16 channel on the slant side. So this side, we attach this sensor is because that a lot of mobile mapping systems or some of the application want to build up the HD map. They used to put the LiDAR on the slant side to see the more of the building itself, like this. If this is the driving direction, so this is actually the point of view, the field of view they're trying to see. So we also attach these two sensors for the mapping purpose. And then we also have the monocular camera in this platform, but we didn't collect monocular camera images in this data set because the bandwidth. But if there is a special request, you say, you really want to monocular data, please do contact us. We can maybe collaborate on this part as well. Okay, so this is the platform itself. So if you see from the top view, then we have the GNSS antenna here. They got different antenna because we've got different receiver use. MAT, F9K, talk about that in a second. And we also have the Novatel 703 GGG antenna over here. This is on the top view. And we put the mobile phone actually on the dashboard over here. So this is the car. So this is a Honda Fit or Honda Jazz, depending on the country that you are, how you code. So we just put the sensors here and antennas here, and all the computer systems is actually in the trunk, in the backside here. So this is our platform. And this is the sensors that we have. So starting with the first one, excuse me. So we have the F9P. F9P is going 1 Hz, and this is the signal that we support. They're supported by F9P. And you can see that the first one is attached with the low-cost patch antenna. And the second F9P, also 1 Hz, is attaching with a Novatel antenna. If you want to study the differences of the two different antenna to F9P, you're welcome to try this. And we also have MAT as well, because this is a very popular version of the U+ chip. A lot of actual system is using this one. So we also use this one here, and you also attach with the low-cost patch antenna, more close to the real applications. And for the phone, we have the Xiaomi 8, which is a Broadcom chip, a dual frequency L1, L5, also coming in 1 Hz as well. And for Novatel, we have the FlashPack 6, and this is the signal that we supported, and of course it's attached with Novatel antenna. And for LiDAR, we have a Veridise 32 channels, 16 channel. We have Laser 16 channel. You can see I already showed you on the two slant side, and also the one on the top. And it's coming at 10 Hz. And for stereo camera, we're using the ED and coming out with 27 Hz. For IMU, Xsense MTI 30 coming with 400 Hz, which is fairly automobile level of IMU. Right. So that's the sensor that we provide. So what kind of data format we provide for each of the sensors? So for GNSS data format, we're using RhinoX 3.03. And we also have the NEMA solution that generated by the vendor itself, by the chip manufacturer or receiver manufacturer itself. So we have RMC, GGA, and GSA for these NEMA solutions and RhinoX. And for IMU, we provide two formats. The first one is the CSV format. CSV format, as you can see, is over here. So we provide the UTC time, GPS week, GPS time, angular velocity, XYZ, acceleration XYZ, orientation XYZ. So that's what we provide for GNSS and IMU. For those of you who are working at the robotic field, maybe you are more familiar with the robotic robotic operation system ROS-back format. So for point cloud, we're using the ROS message, point cloud 2. For image, it's the image message. IMU is the IMU message. Span here also can be read by using the ROS-back message. So for those of you who are working on the robotics, if you want to also read the GNSS data, the RhinoX data into your ROS-back message, you can using another open source code we have. It's called Graph GNSS Sleep. Then it can provide you an access to RhinoX file and push the data to a customized the ROS message as well. So if you cannot find the tool in the GitHub page, the GitHub repo, so just contact us as well. Yep, that's it. And for ground truth system, I would love to mention this because this is urban data, very important. So how do we do that? So we have a Novatel antenna and the span system, of course. And in Hong Kong, we have our core station as well. It's called Hong Kong SatRef. I will talk about this SatRef a little bit more detail. But I quickly, like every station is about 20 kilometers away. So fairly, we can have really short baseline for RTK solutions. And we have the inertial explorer using for post-process to make sure that the ground truth data is good. So the ground truth data is also provided in the format of TST, as you can see over here, pretty standard. And because this is urban, so we do additional manual check. So we're looking at the span result with the image result from the stereo to make sure, okay, so I'm driving in this lane and span is coming out the result in the same lane to make sure that the ground truth is trustworthy. To be honest, we run several different experiments. Like we come up with only 4 data sets, but we run many times. We select only the 4 because this is the 4 trace that we believe that the ground truth is really trustworthy by doing this manual check. That's why we don't have too much. Okay. Then this is for the Hong Kong core station. We didn't provide this data directly in our GitHub repository, but this is because this is a public access. So you can go to, you basically just Google Hong Kong core reference stations or SatRef. You can find this website here. It tells you like how to download the raw data, and the coordinate system is already in the RhinoX as well. And also, if you want to do real time, you have Ntrip, RTCM, they have network RTK, DGNSS as well. It's really well maintained. And it is maintained by the local government, Hong Kong government, and the survey and mapping office. So this is a very good service. If you want to use, go ahead. And if you want to download, if you really don't know where to download, contact us as well. Yes. And the last one is quite special. We also provide the Sky Mask. So Sky Mask is someone who's studying for a 3D MA GNSS, 3D mapping edit GNSS. So we provide a Sky Mask in this format. So for those of you who are not familiar with this is a sky plot, but you can see the gray area here correspond to the obstacle, which is the building in this case. And the blue line here is the Sky Mask we are talking about. So we provide a data set looking like this. So basically, over here in this part, we're doing the clockwise and starting from the north point, which is the heading angle, coming from this, and we come in rotating 1 degree, 1 degree in azimuth angle and 0.1 degree in elevation angle. So to provide you this Sky Mask. Okay, so this is for Sky Mask, and also each Sky Mask is coming out from one particular position. So the center point is a particular position, which is over here. We give a lat long with WGS84 with the height Height is the terrain height that we extract from Google Earth. And then we provide 2 meter separations of each grid point. So each of the grid points is 2 meter separations. So for this is roughly the demo of it. And for 3 different data sets, we have a middle class urban Kenya, harsh urban Kenya, and deep urban Kenya. This is the coverage that we have. This is the coverage that we have. So it actually can go a little bit wider, but we think this is good enough. And this is for SkyMask, the special data that we also provide. Then this is about the sensor, the format, and then it's the calibration. It's very important too. So as we mentioned, this rack itself, we're doing the CAD design ourselves. So we ask a precise manufacturer to support the machinery of it. So and the rack itself is built out of the stainless steel. And this measurement, we talk about measurement. That means the measurement, the extrinsic parameter between these sensors is called the measurement here. The measurement for the CAD drawing is used as an initial guess for calibration method that I will mention later, because you will need to do some optimization to make sure the calibration is good. And for the extrinsic parameter, we suggest that every sensor is going back to IMU for the sensor fusion purpose. So we align the sensor measurement to IMU. So the extrinsic parameter you can get is this LiDAR to IMU, and this camera to this IMU, and also span to this IMU, and also the 16 channel to this IMU. Okay. So starting with the LiDAR extrinsic parameters, so fitting IMU, that's what I mentioned. So for this 32 channel, what we do is we're using a continuous time batch optimization. Basically, we're using the algorithm published in IROS 2020. So we're using the extrinsic parameter from CD drawing as the initial guess. Then we can get this one. We can get this one. And for these 2 16 channels, we're using the multi-LiDAR calibrator in AutoWhale. This is a very well-known open source code for autonomous driving to calibrate the left and right to make it back to the top. So after we make this calibration, you can see that all the point cloud, this is from the left, this is from the right, and this is from the top. Excuse me. Excuse me. Oh, shoot. What did I do? Excuse me. Let me do this again. Okay. I'm sorry. So as you can see, like the point cloud from the left, from the right, everything are aligned really well together. So this is how we do the calibrations for LiDAR. And then for camera, we're using Calib. This is an open source code that provided by a Professor Sigwart from ETH. It's a very popular one. You can come up with the intrinsic camera parameters, extrinsic between IMU as well. So for the extrinsic one, we find out that the left camera and also the right camera of between the IMU, we can get it like a 0.5, roughly 0.5 pixel, and that's the best we can do for now. Yeah. And for GNSS level on, this is the hardest part that we have. So we do not have the precise measurement between for example, between this antenna all the way to IMU. So what we can do is that we're using this, we do the laser ranges to measure the range between this IMU and this. We have a reference anchor point over here. Then we just closely attach the antenna here and to measure the differences between this antenna. So this is the best we can do for now. So this is not only for the patch antenna, for the geodetic antenna over here, we're also using the same method. So we are not so much confident, but we believe that it is within 10 centimeter. So anything more than 10 centimeter, lower than 10 centimeter, we don't really have the confidence. But this is the best we can do for GNSS for now. And talk about for the smartphone. For the smartphone, it's extremely difficult because we put it in the dashboard, right? So this is, we roughly just basically give you, I would say like 0.5 meter accuracy if you're using the smartphone. So smartphone data set, we don't really have the 10 centimeter the accuracy for the ground truth. So we are sorry for that, but this is the best we can do as a university team. Yeah. Right. And for IMU noise calibration, we basically just using Allen variance analysis. We collect data for 2 hours and come up with the noise parameter, and this is the YAML of it. So if you want to have the better measurements, you tell me that this is not good enough. Maybe you want to collect even longer data. 10-hour data, then we can do that and send the data to you to help us to do the calibrations. And you will be listed as a contributor to the data set. We will be very happy for that. Yes. And the last one, I think the last point for the data is about the time synchronization between the onboard ROS computer and the GPS time, because we have to use the ROS to log all the LiDAR and camera, all kind of stuff. So what we're using a Trony. What is Trony? Trony is implementation of NTP. So it synchronizes the system clock with NTP server. In this case, it's our ROS computer to the reference clock GPS time. So we use this one. So how do we do it? So we have the URbanNav MAT receiver on board ROS computer. This is the onboard ROS computer. Basically, we're just using the NEMA plus PPS run UBlocks attached with the onboard computer and make use of Trony to achieve this. We also provide a function for those of you who is not so much familiar with the time convert between UTC and GPS time. So we have this function here. And for the data set, LiDAR, camera, and IMU are putting in the ROS timestamp, which means in UTC. And for GPS time, we have all the GPS receiver timestamp, and ground truths are in GPS timestamp. And one thing we have to mention here is that the wire latency between the sensor that we didn't really tackle in this data set. But we are not driving too fast because this is urban. I will say it can go as fast as like 40 kilometer per hour or 50 kilo per hour. That's the maximum speed we can go with in this urban setting. So I hope it is not too bad. Okay, then talk about the environment, because we're talking about urban stuff, right? So we need to talk about the environment. So we have these 4 different scenarios: middle urban, the urban, harsh urban, and internal. As you can see, like in the middle class urban, this is let me see where this is where we usually start from somewhere here. This is our campus. Then we go out. This is, you can see, starting with Y Street, going to here, a medium Y Street. This is a typical very high one side street, and on the right hand side, this is a bit like a park. So you have some trees on the right hand side and a wide intersections and coming back. So this is the point cloud map that we generate of all the LiDAR point cloud, and also fused with span systems. So this is what does it look like. And for the deep urban Kenya, we're starting also with the sky, the open sky. I think it's on here, then coming down to the tunnel, then going down Y Street. This is relatively easy. Then coming to here is very difficult. It's residential area, but really high buildings, 80 floor something, very high. And you have a lot of double deck bus driving in between, then coming to here, then middle class urban, then coming back. And for this data set, it's very interesting. Like we're starting with somewhere opened, then we do a drive a very long time. Then we find in some of the time the rest of the part didn't show in the figure. That means the ground truth, we are not really believing that. We don't believe that the ground truth is good, because we're looking at the camera images, we're looking at the span system. It doesn't really match. So this is the part that we are confident that the span system is coming out with the good result. Because this environment is crazy. It's a lot of people working, a lot of double deck bus, a lot of high building. So this is really tough even for span system. But this is the part that we extracted. We believe is trustworthy. Okay. Then the last one is from the open skies environment, and then all the way come to the cross tunnel between the 2 islands in Hong Kong, and coming out to an open sky area as well. So this is a very long tunnel. If you look at the length of the data, because this is very much I mean, like robotics people, they care about this quite a lot. How long is the data? So it's all about 3 to 5 kilometers, 3 to 5 kilometers. And we also come up with the indicator for the environment. We call it sky mask indicator. How do we calculate this? So we have sky mask like this. Then we have all the azimuth angles, 360 degree. In each of the azimuth angle, we have an elevation angle mask, which is this degree. We calculate the average of all this circle and put out with one number. We call it mu, MEA. So this is the number we use. You can see like this is about 45 degree, 47 degree, 55 degree. So it looked like not so much, but if you're looking at the figure, we are talking about most of the environment are only within this circle. So this is a really challenging data set, I would say, yeah. And this is what does it look like. Driving, you can see this is a LiDAR point cloud, and this is the environment within the driving. From the right hand side, you can see this is a lot of trees over here, one side building. If you're looking at the sky pointing camera here, so this is a virtual sky pointing camera that generated using Google Earth. We're using the script provided by Taro Suzuki. Thank you for that. You can see like it's really challenging. This is only the middle class urban Kenya. You can see sometimes you even have road bridges as well, and all the signals are quite blocked. And for the urban Kenya, this one is very interesting. We're starting with the open sky environment. You can see in the beginning it's not too bad, not too bad. And 1 second, let me stop. Give me a second. And all the way come to here, if you come to the middle side, it's going to like a crazy environment like this, very, very narrow. So you have a very narrow street, and within the street, sometimes if you look at on the image size, you have lots of cars as well. Let me see. We come to here, some double-deck bus coming in, very narrow streets, double-deck bus coming in. So very challenging environment as well. The last one, harsh one is starting from the beginning. We are looking like this, very, very extremely challenging. This is extremely challenging, and a lot of vehicle, a lot of pedestrian walking around. It's, I believe this is one of the toughest scenario we can have in urban. And the last one is for the tunnel. So tunnel, we don't have sky pointing camera, so because it's all blocked. You can see very repetitive features with some vehicle driving around. Very repetitive. Look at this again. You see the point cloud, very repetitive, and the camera is very, very difficult. Okay, and then this is all about the environment and data. So I want to show you what does it look like in our GitHub repo. So if you go and Google UrbanNav dataset, you will find out this link. So this is the main table we have. On the left-hand side, talk about all the detail of different scenario. If you're clicking, you will see all the detail. I will show you in the next page. And on here, you can have all the data, like LiDAR, stereo camera, IMU using RAS, GNSS, and also sky mask over here, ground truth over here. You have the point cloud over here if you click it. And then if you click in one of the scenario, this is what does it look like. So the demo image is what we show here. That you just see, I show in the presentation. And here we give you a lat long to know roughly where it is in the Google map. So you can put in to see the street view, understand the environment look like. And then we also provide an extrinsic parameter over here, and IMU noise over here, and also for robotic, the ROSBAC, and for, for GNSS Rhinex 3.03, NIMAD, and also ground truth, you can all find in this page. Okay. Finally, I want to talk about some performance using the open source code. So we're using the most popular one, so which is in GNSS 3, you must know RTK-lib. So we're doing only the weighted square, the SPP, the RTK-lib SPP, and we also enable the outlier rejections, which is the typical setting for RTK-lib. Okay, so you can see in this free environment, the behavior is very different. For FlashPack, you usually have the lowest availability. So, but it has the best mean and standard deviation over here. So the reason we believe, we didn't really dig out to see what's going on, but the reason we believe is that the FlashPack, they usually have better antenna, right? So it resists more multipass. The sensitivity is getting lower compared to this commercial receiver, like U-Blocks and also like Xiaomi. So the sensitivity is lower. So ending up, they come up with much more healthy data compared to those commercial receiver. For the commercial receiver, you can see it's usually standing in between. For Xiaomi, you can see that the mean and standard deviation is always the largest. It's always the largest. Yes, and yeah, for the rest is pretty normal. But this is very interesting here. Like the availability is very low for this harsh urban Kenya. The reason for that, we believe, is also because the outlier rejections algorithm in RTK-lib, they actually reject a lot of measurements from these two receivers, resulting this low availability. So, by the way, so the definition of the availability is that within all the epoch, how many single point solution that I have. So this is for the GNSS single point position result. You can see it's actually showing that the data set is very challenging. And for vision odometry, we try Beams Fusion. It's developed by UST, Dr. Shen Shaojie, very popular one. So we evaluate using EVO, only looking at the relative pose error between two epochs at a time. So bear in mind, this is 27 hertz, 27 hertz. So this is between two epochs. In some of the time, you can see two epochs, it can already come to 50 centimeter of error, 30 centimeter of error, 50 centimeter in this environment. And internal it fail because the repetitive repetitive features that we observe. And looking at the max error, so between two epochs, two images, sometimes you can go to a meter of error. This is definitely coming from the dynamic object we're seeing in the images. So it's very challenging. And for LiDAR odometry, we're using LeoSLAM, which is also a very popular one. So this is about 10 hertz. Comparing, this is 10 hertz. So in 0.1 second of the time, so it can come up with only 14 centimeter of error, 8 centimeter of error, 7 centimeter of error. And this is the reason why LiDAR is a very popular sensor for autonomous driving in urban Kenya, because it can come out much more robust comparing to the images data. And you can see the maximum error between 0.1 second is only 2 meters. This case is 7 meters because, again, dynamic objects. And it also failed internal as well. 2 nodes as well. Right, so here comes to my conclusions. So we come up with the open source multi-sensory dataset in urban Kenya with LiDAR, camera, GNSS, NS, and these are included. And we have more benchmark method in the paper, so go ahead and check it. So we come up with this conclusion. So GNSS can do absolute positioning, relative positioning, of course. If you have Doppler, TDCP, you can do that. And this is the performance that we got better in urban Kenya, middle class, deep, harsh, die. LiDAR, good. Repetitive and die. Camera, not so good. It's actually pretty good in this one if you go and check the paper. In some of the visual odometry actually survive internal, but the performance is really bad as well. And of course, unless you can always have the solutions. Then I want to share additional few pages on lesson learned. So when we're trying to collect this data set, we realize a very interesting challenges. So we put this stereo camera here. So like the electrical shutter of these CMOS cameras, it actually sometimes operating a frequency they're very close to use by GNSS signal. So there are many times we go out to collect the data and coming back, then our span system die. We didn't receive any signal. They just come out no signal at all. After we drive, no signal. We realize this is the problem. So in the end, we put up a copper foil here to trying to kind of like stop the electrical interferences. Sometimes it's good, sometimes it's not good. So if you buy a stereo camera that have very similar CMOS frequency with GNSS signal, you gotta have problems. Second thing is that you must know that you definitely have to go to open sky area, then get a very good fix, waiting for 10 minutes, then starting to drive. So that's the second thing that we learned. The third thing is that we figure out like it's really useful that when you're trying to open source the data, then you have to provide a pilot data set first. So we have a first pilot data set with only 2 traces. Then we collect a lot of feedback from our friend. We send it to our friend and ask them to use it and see what's going on. And then you come up with the official one, which is kind of more robust and more reliable. And this is really good for developing an open source code, open source data. So almost finished. Bear with me for a few minutes. So this is currently the research institute that use UrbanNav. We have a lot of people from mainland China using it. A Japanese partner like Chiba Institute of Technology, obviously is from Taro Suzuki, and we have people from Calgary, Arizona State, Stanford, Purdue, and also from Bonn, from Munich Technical University in Chimes, Mongolia. So lots of people are using it. So we are very happy. As you can see, like there's more stars going up for these 2 data sets. So we're looking forward to see more people using this one and benchmark their positioning performance using the same data set. Finally, I would love to say, if you are a passionate in smartphone data, please go ahead and try this smartphone decimeter challenge 2023. So the deadline for these competitions is May 23rd. And we have a lot of data there. We have a lot of carrier phase, and we have different phone. We have Pixel phone, Samsung, and Xiaomi phone, and we have 196 traces with super trustworthy ground truth. In Google, they have the liver arm, the robotic liver arm, to do the really precise measurement of the span system all the way to different form. So that's something that's really hard for us to have it. But Google open source this. Please go ahead and use this one. It's very interesting. And if you got the really good performance, you get a cash prize as well. And we got to meet you in ION GNSS Plus 2024 in Baltimore. So please, if you do come to these conferences and join us, we'd love to see you there. Okay. I want to talk one last slide. I know I'm talking too much, but one last slide. So I want to talk about how good of this SDC. We have such a price in cash. Last year, I think we have only 10,000, but this year is 15,000. Very good. And we 3 teams can come to ION GNSS Plus, and you can the hotel registrations are all included. And we are not only have the high-end phone, those very challenging low-end phone, the Samsung A series, L1 only. It's very challenging. So if you do want to see how good your algorithm happens in real smartphone data, and please do try this data set and submit your result to Gago. And the data set is collecting in California, both in Los Angeles and also in San Francisco areas. So it's mainly on the highway. So we want you to demo that if you can receive good performance, sub-meter performance, maybe even 50 centimeter performance using a smartphone data. If you can do that, we'll be really proud of you and probably talk to you on how do you do this. That's the goal. Okay, so that's all for me. Thank you for bearing with me these 40 minutes. And if you have any questions, I'm ready to take.
Thank you, Dr. Xu, for this great presentation. We will now start transitioning into Q&A, so we will accept questions from the audience. As a reminder, you can submit your questions using the Q&A button in your viewer. So it looks like we have some rolling in right now, so we can just go ahead and get the ball rolling on this. Dr. Xu, what 3D build models were used to generate the sky mask, and what's the accuracy of the model?
Okay, so this is a great question. So like the 3D model we use is actually maintained by the local government, the land department of the local government. They have the street view car, they have the aerial image. They also do their own optimization fusing to come up with this 3D building model and widely available for the public use. And the accuracy, horizontal and vertical, they claim is about 1 meter. It's about 1 meter. That's how I use for 3D building model. Yep, that's the first questions.
Great. Okay, so we have another question here. Someone is saying that they used the dataset before, and they would like to say thank you for making it public.
Yes.
Does Hong Kong have a plan to have 3D city maps or HD maps? And does your team plan to create anything like this and make it available with the dataset?
This is a really good questions. Like for 3D building model, because it is actually already widely it's publicly accessible. As I mentioned, it's provided by land department, so we won't provide it directly, but we can provide a link for you to download those data set. But it's a bit challenging because you know, like in 3D model, they have a different format. You may need to figure out how to transform the different 3D models and put it into GNSS one. It's actually quite challenges in a way. Yeah, and for HD map, we actually trying to open source a code using the data set I just mentioned and with the image that I just mentioned to come up with the HD map. But HD map is full of different vector features. For example, we recently going to publish one paper in IET, and then in that paper we open source automatic generate the landmarking of the data, but not in this difficult environment, not in this urban environment. So we do it in like a suburban environment, we can achieve that. But in this urban environment, I think it's still quite open challenges because even for mobile mapping system coming to this area, you need to come up with those detail of HD, the vector feature. It's really hard. But the question is, do we have a plan? Yeah, we always have a plan to provide more data and more features to this community. So we will try to do it, but I cannot promise any timeline. Hopefully that I can answer your questions.
Okay, we have another one here. Do you also collect the raw INQ samples for GNSS signals? And they want to ask this because you've presented DPE paperwork for Urban HK.
Oh, that's a much bigger ask because the data set is really huge. But we can think about this. We can think about this. But I do know, like in Shanghai Jiaotong, they also have a really good data. I'm not sure if they open source or not. If we have colleagues in Shanghai Jiaotong here, maybe maybe you can come raise your hand and answer that. But I do know they have really good data set with IQ. They have the really good car and logging those IQ sample in urban area as well. I see a couple presentation from them. But to answer your questions, yeah, I will think about it. I will think about it. If the demand is strong, that I can discuss with the team. Maybe we can come up with this. If we want to do this together with LiDAR, it's a lot of work as well. But we will think about this. Thank you for your inquiry and interest.
Okay, and we have another one here. What's different from the popular KITTI and Waymo datasets?
Oh, yes. So like those KT dataset and also Waymo dataset, they don't really provide the raw level, which means the pseudo range and carrier phase, carrier to noise ratio level of GNSS measurement. They basically usually just give it as a point, which is the ME and the NEMA solutions. So because this is I'm coming from GNSS society community, so I would love to share this because those robotics guys, they didn't focus so much as we do here in ION. So that's the differences made. And also for Kitty data set, the environment is really suburban. It's quite a simple data set. Yeah. Okay.
And how many datasets do you have for Tokyo?
For Tokyo, I believe we have two data sets. We have two data sets. Maybe I can share this. I believe we have two data sets. I'm not sure if Taro is. If you go and check this UrbanNav, let me see. You should have TED, one in Odaiba and one in I think central Tokyo. Excuse me. Oh, give me a second. If you come to this website, this is our UrbanNav dataset. For the Tokyo dataset, if you scroll down, Tokyo dataset, yeah, we have two dataset here. One in Shinjuku, one in Odaiba. So this one is much more challenging. This one I think is pretty harsh as well. And this one is like a middle class urban Kenya. So if you're interested about this, maybe we can ask Taro to do one, to do one talk for you guys. Yeah. Okay.
Okay, next question. Is there any repetitive data collected along the same route on different dates? Such data would be useful for dividing the data set into training and testing sets.
Great questions. That's very important. So like I think everyone can see my screen, right? Yes. So over here we have 6 data sets. With 6 data sets. In fact, these two pilot data sets are all collected in the middle class urban Kenya. So these two pilot data sets are kind of repetitive to this one. No, I think. Sorry, this one. I think this one. I'm sorry. I need to confirm this. Darren, if you are here, you can raise your hand to come out to say me here. But I think this one is the middle class urban Kenya. And then if you go down. This one is in the night. So what is interesting, like we collect the data in the night as well. So we have two middle class urban Kenya data sets driving in the same route, but one is in the night, one is in the morning. So as you said, this is going to be very interesting to compare the two. Yeah, and I hear you. So if we can have like in the same environment, same different date, but the repetitive route, that would be interesting too. So I will consider that as well. So we do plan to keep invest on this UrbanNav data set. Thank you.
Thank you. Let's see here. We have a couple more.
Okay.
Okay. So someone says, what's the factor blocking you in collecting more data sets? So they give, for example, Google SDC has 200 data sets.
That's a great question. Money and sponsorship. You know, like in the university, we as students, like they collect data wherever needed, right? But when we're trying to publish, I mean, we need to maintain this. We need to make sure the quality to the best. It really taking us a lot of time and effort. But But I recently have a thought is that I probably want to write some project to ask for to write a proposal to ask from different funding agency, whether it's government or industry, to have a campaign of 30 kilometers of drive or even more, 100 kilometers of drive of this kind of data set. So if I can get it funded, I will definitely share to the community again. So this is in my ambition for the next 2-3 years to get funding and trying to get it rolling with the much longer one, and hope this can be become one of the really good arena for people who also passionate at urban navigation. So I do have the plan. So, but I need money. That's the factor. Yeah.
Okay, another question. At what level is the GNSS solution availability considered? Like when raw measurements are available or receivers positioning output or any other enhanced pre-processed solutions?
Yes. So we have the right next one, which is including the right next 3.03, right? So that means you have the pseudo range, Doppler frequency, carrier phase, and carrier to noise ratio. And for the point solution one, we have the NEMA solution as well. The NEMA solution meaning like directly give you lat long of the position, lat long height of the position. So the two levels are provided, but we didn't really provide the RF and IF level of measurement, the IQ, as asked by different the attendee here. Yeah, so we have the right next level, I would say. Yeah.
Okay, we have one last question. Let's see. We have also done RTK experiments using the Accord Make IGS receiver. From the data observed that some satellite signal strength received, but the azimuth and elevation angles recorded as 0. Does this make sense? Can you explain this?
It doesn't make sense to me, but I don't know what happened there. It looked like a bug to me, but I don't know why. Hope I can help more, but maybe you can email me to show me more detail. Maybe I can answer much better. But it looked like a bug to me. Yeah.
Okay. Well, that is all we have for Q&A. So thank you for joining us for today's webinar, and thank you, Dr. Xu, for your time and preparation. We want to remind everyone that a recording of the webinar will be posted to our website, YouTube channel, and social media channels by Friday the 3rd, so this Friday. That'll be available for everyone that attended. And please feel free to share that as well. But thanks again, and we look forward to having you join us for a future ION webinar.
One last comment. So I will also post the slide in the GitHub repo. So the detail you hear here can be found in the Git repo of the UrbanNav dataset. That's all. Thank you guys.
Perfect. Thank you, everyone.
Thank you. Bye.